All living things on planet Earth, from microbes to whales, can be categorized into a single hierarchical system. This system has been developed over the last 300 years. Layers have been added, and there's been debates as to what creatures should go where. However, it's proved an incredibly useful way to understand how all life is connected. Learn more about the system of biological taxonomy and the tree of life on this episode of Everything Everywhere Daily. This episode is sponsored by Quince. Vacation season is nearly upon us, and you've heard me talk before about my favorite blanket and towels that I got from Quince. But did you know that they also have a collection of great travel products, like lightweight shirts and shorts from just $30, pants for any occasion, and comfortable lounge sets? They also have premium luggage options and durable duffel bags to carry everything in. The best part? All Quince items are priced 50 to 80% less than similar brands. By partnering directly with top factories, Quince cuts out the cost of the middleman and passes the savings on to us. And Quince only works with factories that use safe, ethical, and responsible manufacturing practices and premium fabrics and finishes. For your next trip, treat yourself to the luxury upgrades that you deserve from Quince. Go to quince.com/daily for 365-day returns, plus free shipping on your order. That's QUINCE.com/daily to get free shipping and 365-day returns. Quince.com/daily.
This episode is brought to you by State Farm. You might say all kinds of stuff when things go wrong, but these are the words you really need to remember. Like a good neighbor, State Farm is there. They've got options to fit your unique insurance needs, meaning you can talk to your agent to choose the coverage you need. Have coverage options to protect the things you value most. File a claim right on the State Farm mobile app, and even reach a real person when you need to talk to someone. Like a good neighbor, State Farm is there.
You're probably aware that the scientific name for human beings is Homo sapien. This system of two Latin words to describe a biological species was developed almost 300 years ago and has been adapted over time to accommodate seismic shifts in biology, including the discoveries of natural selection and DNA. Before our current system, the classification of living organisms was largely informal, unstandardized, and based on practical or symbolic qualities rather than systematic principles. Ancient Greek philosophers such as Aristotle made early attempts at categorization. They grouped animals by characteristics such as habitat, land, air, water, and physical traits, blooded versus bloodless. Plants were often classified based on their uses, medicinal, culinary, or agricultural, especially in works by Theophrastus, Aristotle's student and the man who's considered the father of botany. In the medieval period, scholars like Albertus Magnus and Islamic naturalists such as Al-Jahiz observed observations but still relied on descriptive, often theological frameworks. Often these early systems lack consistency, universal names, and a clear hierarchy, focusing more on utility or symbolism rather than on natural relationships. The person credited with the foundation of the system that we use today is the Swedish naturalist Carl Linnaeus. Linnaeus was born on May 13, 1707, in Roshult, Sweden, to Nils Ingmarsson Linnaeus, a Lutheran minister and amateur botanist, and Christina Brodersonia. From an early age, Linnaeus developed a fascination with plants, encouraged by his father, who maintained a garden for medicinal and culinary plants. Initially destined for the clergy, Linnaeus showed little interest in religious studies. His early teachers recognized his aptitude for botany, particularly Dr. Johann Rothman, who encouraged him to pursue medicine at Lund University, which he entered in 1727. A year later, he transferred to Uppsala University, where he studied medicine and lectured in botany despite being only a student. Linnaeus' scientific reputation grew through several expeditions, including the Lapland Expedition of 1732 and the Dalarna Expedition of 1734. During these expeditions, he collected samples and wrote about his observations. From 1735 to 1738, Linnaeus stayed in the Netherlands, England, and France, interacting with leading naturalists and examining major collections. These visits helped him develop relationships that would help spread his taxonomic system throughout Europe later on. To understand Linnaeus's impact on biology, one must appreciate the chaotic state of biological naming before his system. Before Linnaeus, organisms were often identified with polynomial names, lengthy Latin descriptive phrases, often 10 to 12 words. Different naturalists used different systems, making communication difficult. The same organism might have multiple names across regions and languages, causing tremendous confusion in scientific literature. European exploration had dramatically increased the number of known species, rendering existing classification approaches inadequate. Collections from the Americas, Africa, and Asia introduced thousands of new specimens that required systematic organization. Linnaeus's systematic reforms addressed these problems through several innovations. The first was binomal nomenclature. Linnaeus's most enduring contribution was binomal nomenclature, the two-part naming system still used today. Each organism receives a genus name, which is always capitalized, and a species name, which is always lowercase. Both are written in Latin and are italicized whenever they are written. The elegant solution replaced unwieldy polynomials with concise standardized names like Homo sapien. While not entirely original, some predecessors had experimented with similar approaches. Linnaeus consistently applied the system across all organisms. He codified it for animals in the 10th edition of his book Systema Naturae in 1758 and for plants in Species Plantarum in 1753. His other major innovation was creating a formalized, nested hierarchy of taxonomic ranks. His original ranks were kingdom, class, order, genus, species. If you have encountered the taxonomy system in school, this is slightly different than the one that you're probably familiar with. More on that in a bit. Linnaeus' system was a good start, but it wasn't perfect. The rank of family began to be used around the late 18th and early 19th centuries, with its first formal uses by naturalists like Pierre-André Latérale, a French entomologist in the early 1800s. As more species and genera were discovered, some genera were more closely related to each other than to other genera, prompting a need for an intermediate category between order and genus. The category of family helped organize genera that shared apparent morphological or genetic affinities, allowing for a finer resolution in taxonomy. And it became particularly useful in botany and zoology for grouping related genera. The rank of phylum was formally introduced in the mid-19th century, particularly by German biologist Ernst Haeckel in the 1860s. As more diverse organisms were discovered and studied, particularly among invertebrates, it became clear that some groups were too broad to be lumped together under a single class, and too distinct to be merely subdivisions. The rank of phylum was introduced to reflect major structural and developmental differences between animals. It provided a higher-level category to accommodate large evolutionary divergences. With the addition of phylum and family, it created the system that many of you, including myself, grew up knowing. Kingdom, phylum, class, order, family, genus, species. However, there was one more layer that was necessary. The rank of domain was introduced by Carl Woese and George Fox in 1990, based on ribosomal RNA sequence analysis. Advances in molecular biology revealed profound genetic differences amongst prokaryotes that were not apparent from morphology alone. Prokaryotes being single-celled organisms without a nucleus. Woese discovered that what had been thought of as a single group of simple prokaryotes, bacteria, actually contained two fundamentally distinct lineages, bacteria and archaea. These, along with eukarya, which are all organisms with complex cells and a nucleus, were placed into a new higher rank above kingdom called domain. This three-domain system more accurately reflects deep evolutionary divisions at the cellular and molecular levels. This 8-level system is our current one, and it works pretty well. However, it too isn't perfect. One major issue is the existence of paraphyletic groups, where a taxonomic group excludes some descendants of a common ancestor. For example, reptiles traditionally exclude birds, even though birds evolved from theropod dinosaurs. This results in a classification that does not reflect true evolutionary history unless birds are included with reptiles, which challenges long-standing educational and cultural perspectives of what a reptile is. Another problem is the phenomenon of convergent evolution, where unrelated organisms independently evolve similar traits. This can mislead taxonomists, especially when relying on morphological characteristics. A classic case is the similarity between dolphins, which are mammals, and ichthyosaurs, which are extinct marine reptiles, both of which developed streamlined bodies, dorsal fins, and flippers due to similar aquatic lifestyles, despite being only distantly related. Earlier classifications often place such organisms closer together than was warranted based solely on appearance. The concept of species itself presents difficulties. In sexually reproducing animals, the biological species concept defines species as a group that can interbreed and produce fertile offspring. However, this definition breaks down in cases like ring species, such as the Larus gulls around the Arctic Circle, where neighboring populations can interbreed, but the end populations in the ring cannot, despite gene flow existing between intermediate groups. This makes it hard to draw a clear line where one species ends and another begins. Similarly, in asexual organisms like bacteria, the species concept becomes even more ambiguous, as reproduction does not involve interbreeding. Bacteria species are often defined by genetic similarity thresholds, which can be somewhat arbitrary. Horizontal gene transfer in prokaryotes further complicates microbial classification. Genes can move laterally between unrelated bacterial lineages, blurring the lines of descent that classification systems try to capture. This means that a bacterial species might possess genes acquired from vastly different branches on the tree of life, making phylogenetic trees appear more like webs or a network. While DNA sequencing provides powerful tools to assess relationships, it can also overturn long-accepted groupings. For example, the traditional kingdom Protista was shown to be polyphyletic, meaning it included organisms that did not share a recently common ancestor. With the time remaining, I'd like to go over some of the top-tier groupings on the tree of life. Complete coverage of every level of the tree would be impossible, even if I had an entire lifetime. I'll briefly go over some of the relevant groups, and I may possibly do some of these groups as entire episodes in the future. There are estimated to be somewhere between 3 and over 100 million species on Earth, with a commonly cited figure of around 8.7 million species. And those are just the eukaryotes. Once you get into bacteria and archaea, it's difficult to even make an estimate because the dividing line between one species and another can be so hard. So, as I previously mentioned, there are 3 domains: bacteria, archaea, and eukaryotes. Bacteria and archaea are both single-celled, prokaryotic organisms, meaning that they lack a nucleus and membrane-bound organelles. But they differ slightly in their genetic makeup, biochemistry, and evolutionary history. Bacteria have cell walls made of peptidoglycan, while archaea lack peptidoglycan and instead have unique lipid membranes and cell wall structures. Genetically, archaea are more closely related to eukaryotes than to bacteria, particularly in their mechanisms of DNA replication and protein creation. Additionally, many archaea thrive in extreme environments such as hot springs, salt lakes, or acidic habitats, even though they also exist in more common settings. Eukaryotes are what most of us are familiar with. Every life form we can observe and experience with our senses is a eukaryote. There are 4-ish kingdoms under the eukarya domain. They are fungi, Animalia, Plantae, and Protista. And I say 4-ish because of the Protist kingdom, which consists of single-celled eukaryotes such as amoeba, is currently under a great deal of debate, with some splitting it into multiple kingdoms. Fungi includes all mushroom, fungus, and lichens. Plants include all multicellular, photosynthetic organisms with cell walls made of cellulose. Animals are multicellular, heterotrophic organisms that consume organic material, typically with specialized tissues and the ability to move at some stage of life. This includes all animals, from sponges all the way to humans. So if we were to take every level of classification and put it all together, what would be the complete classification for human beings? We are in domain Eukarya, kingdom Animalia, phylum Chordata, subphylum Vertebrata, class Mammalia, order Primates, family Hominid, genus Homo, species Homo sapiens. The biological taxonomy system is a human attempt to organize a dynamic and often messy natural world. It isn't perfect, and there are often debates about how life forms should be classified. Nonetheless, it's a pretty robust system that helps us to understand the natural world and has been doing so for almost 300 years. The executive producer of Everything Everywhere Daily is Charles Daniel. The associate producers are Austin Oakton and Cameron Kiefer. I want to thank everyone who supports the show over on Patreon. Your support helps make this podcast possible. I'd also like to thank all the members of the Everything Everywhere community who are active on the Facebook group and the Discord server. If you'd like to join in the discussion, there are links to both in the show notes. And as always, if you leave a review or send me a boostagram, you too can have it read on the show.